Hello and welcome to CMG's webinar on What's New in General Release 2017. My name is Anjani Kumar. I'm the Vice President of Engineering Solutions and Marketing at CMG. I'll be the moderator for today's session. I'm pleased to introduce Greg Warren, Reservoir Simulation Engineer at CMG, who will be presenting today's webinar. Greg has been with CMG for 4 years, and he specializes in thermal recovery processes as well as unconventional reservoirs, including hydraulic fracture modeling and EOR in unconventionals. He also has an extensive experience in advanced thermal wellbore modeling and design using FlexWell and flow control devices. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. We have tons of new exciting features in the 2017 version, and I hope that today's presentation will be useful to you. Over to you, Greg.
Thanks, Anjani. So again, today's webinar is focused on CMG's 2017 general release, highlighting the new features and improvements that we've made for this year. And as is always the case with the What's New webinars, we don't have time to cover everything today. So for more information, please refer to our supporting documentation, such as the software highlights document that will be included in the CMG installation folder and also available on our website, as well as the product manuals, which go over the what's new features for each specific product. So the layout for this webinar is going to be similar to the what's new for last year. First, we're going to go over the common simulator enhancements, and then we're going to talk about the individual product improvements, being the 3 simulators, IMEX, Gem, and STARS. And then we're going to go over CMOST AI, and then the improvements to our pre- and post-processing softwares, Builder and Results. We'll talk about the improvements to our fluid characterization software, WinProp, and then we'll go over some of the supporting CAS software, including cEdit. So some of the focus areas where we've tried to improve on for 2017 have been, first, improving the speed and performance along the entire reservoir simulation workflow, from pre-processing using Builder to improving the runtime of our simulators to post-processing using results. And a second main area of focus has been expanding on the features of CMG's new results software, making it able to completely replace its predecessors, Results Graph and Results 3D. First, we'll go over the common simulator enhancements. So the first couple of options that we're going to talk about today are numerical performance enhancements to improve the run times of our simulators. And so the problems that we've been simulating have been getting more and more complex over time. We tend to use more and more grid blocks in our model. The biggest models are getting larger and larger, and also the processes that we're modeling are becoming more advanced. And this brings rise to more components in our models, perhaps more reactions, and also perhaps more relative permeability data. And all of this added complexity has brought rise to the need for numerical tuning more often. And numerical tuning does require some experience. We have to know and understand the numerical keywords that we're changing. We have to know what values to change them to. And then it also does take some time, because we have to run some trial and error tests to see if our theories on which numerical parameters will actually help. So in order to help address this, a couple of years ago, CMG provided an automated tuning workflow using CMOST AI for numerical tuning. And essentially what this workflow did was you could give a list of numerical parameters and the values that they could take on to an automated optimizer, being CMOST AI, and it would try to intelligently search for the best combination of these parameters and values they can take on to get you the best combination of, for example, fast runtime and low material balance error. And this process was much better than the manual approach, but still did take some time and knowledge of how to use CMOST and set this up. So CMG in 2017 has taken numerical tuning to the next level with the introduction of a new keyword called auto-tune. And this auto-tune feature is a big shift in how numerical tuning can be done. And what it does is it introduces simulator internal numerical tuning and can be implemented by inserting only one keyword into your data set. So when you add that one keyword, being auto-tune, your simulator is going to use internal artificial intelligence-based adaptive time stepping to control the time step size selection, as well as various other internal numerical parameters. And with this, the simulators do all of the work for you. You just have to add one keyword and run one simulation run. And this was implemented to save engineers time, not only by having to spend as much time learning about what the numerical parameters do and changing them and running trial and error tests. You also don't have to wait as long for that first job to finish if you apply AutoTune. And really, this lets reservoir engineers focus on the reservoir engineering aspect of simulation. We can understand and control the inputs that we're putting into the tool. We can understand the options we're using, and then we can understand the outputs and analyze the results from the tool as well. So on this slide, we're showing some of the performance gains that we've seen using AutoTune. And we're showing it in this bar chart here. And on the y-axis, we have the speed-up multiplier shown. And the speed-up multiplier is described as the simulator runtime using the AutoTune feature divided by the simulator runtime for the simulator default numerical settings. So for example, a value of 1 here would mean that with using AutoTune, it ran the same speed as using the defaults. A value of less than 1 would mean that it ran slower, and greater than 1 means that AutoTune was faster. So for example, the first data set we have represented here, say D1, ran about 2.5 times faster using AutoTune. And then on the x-axis, we have a variety of processes represented, and then the red bars represent star simulations, and the green bars represent gem simulations. And so this new option is available currently in stars and gem, will be available in IMEX as well shortly. So we have, on average, seen the models run 3 times faster using AutoTune. And we, of course, haven't represented all of the tests that we've run on this chart. And we're seeing from our internal tests as well as client tests who have been early adopters of the 2017 release, seen speedups of greater than 10 times as well. And so we can see from the x-axis that a wide range of processes do benefit from using AutoTune. For example, in stars, we have several SEG-D data sets represented here, as well as a chemical EOR process being an alkaline surfactant polymer flood. And then in GEM, we're seeing consistent speedups, for example, for CO2 flooding, as well as primary production and tight oil or unconventional cases. And of course, the speedup that you actually realize using AutoTune is going to be model and process dependent. But currently, the vast majority of data sets that we're testing this on are showing speedup, and it's at least greater than 90% of the data sets we tested on. And this being a relatively new option, we're still kind of trying to optimize the algorithm to be able to accurately identify which process is being modeled in each simulation, and then apply process-specific numerical tuning parameters to get you the best speedup possible for each particular data set. The next numerical performance enhancement that we'll talk about is an improvement to CMG's linear solver, which is essentially the core of how we solve the reservoir simulation problem. So combinative is the new feature, and it's the next step in the evolution of CMG's linear solver, and it improves on what is already the fastest simulation software in the industry. So we're, again, representing some of the performance gains we've seen using this new combinative option in the chart shown here. This time we have simulation runtime on the y-axis, and then again, a variety of processes that we've modeled, which are each specific data sets on the x-axis. And then for each model, we have 2 bars shown. One is the new combinative option in green, and then one is the linear solver option that we've been using up to this case, and is still, or sorry, up to this time, and is still available now, called the ILU linear solver. And then above each set of bars, we have the speed-up multiplier also, which is defined the same as on the previous slide. It's the combinative runtime divided by the runtime using ILU. So this new combinative option is very good for a particular subset of simulation problems, and particularly those are problems that are very non-linear in their solutions nature, or very complex data sets that would have been otherwise fairly difficult to get a reasonable speed up on from numerical tuning. So for example, we'll start by talking about this water flood case shown in the middle here, which ran 2.2 times faster using combinative compared to the ILU solver. And on this particular water flood case, we would have had a lot of mobile water present in the reservoir, which comes about due to the initial water saturation definition, as well as the initial relative permeability for the connate or critical water. So we would have had water able to move in the reservoir, And then we would have, when we introduced a pressure change into this model, we would have had a large pressure change go throughout the entire reservoir, or a sharp pressure front move quite quickly through the reservoir. And this type of problem combinative is particularly good at solving, hence why we get a good speed up using combinative. We also have 3 SEG-D datasets being represented here. All of them happen to be using FlexWell, and the fastest of the 3 is this SEG-D FlexWell 3 case, which ran 7.2 times faster using combinative, again, compared to the ILU solver. And these 3 SEG-D datasets, again, would have had mobile water present. So as soon as the steam chamber started to grow, we would have had a large pressure front moving throughout the reservoir, and combinative is good at solving that. And then finally, we have a tight oil case over here on the right, which went 1.5 times faster using combinative. And this particular tight oil case would have been a dual continuum model, or using CMG's dual porosity or dual permeability options. And combinative, we found, is showing consistent speedups for these types of models as well, if you're using the dual continuum models in particularly unconventional cases. Combinative is currently available in IMEX and STARS, with GEM not far behind in development of using this option, so it should be available on that simulator as well shortly. Next, we'll talk about a few unconventional modeling improvements that CMG has made for this year. So CMG has a very extensive workflow for modeling unconventional reservoirs and hydraulic fractures. For example, we have several ways we can define hydraulic fractures, the first of which is bi-wing fractures or planar fractures. And in this method, we define a fracture half length and a height and a fracture width. We can also import microseismic data and SRV data for defining complex hydraulic fracture networks. And third, if you've modeled your hydraulic fractures, whether they're planar or complex networks, in third-party software, and you want to import that into our flow simulator to do some history matching or some forecasting, we also allow and assist with the importing of that third-party hydraulic fracture definition into our flow simulator. So again, CMG has taken one of its strong workflows and made it one step further and better this year by adding a new hydraulic fracture initiation and propagation tool into a flow simulator. And this is unique and the first of its kind in the market. So this actually lets us model the creation of hydraulic fractures instead of defining them using some predefined half lengths and widths and heights, for example. And this is done by coupling our geomechanics module to our reservoir flow simulator. And so when we actually start injecting some fracture fluid, we'll inject at a certain pressure and a certain volume of that fracture fluid, and that fluid will have certain properties. And that's going to be used by the geomechanics module to determine the minimum effective stress. And if we cross the threshold for hydraulic fracture formation within the geomechanics grid, we can see the nodes of the grid block split open, and we can see the hydraulic fracture being formed. And then this can be translated to a permeability increase in the flow simulator. And so you can see from the image on the slide, we can actually visualize this process as well. So this is kind of a video taken from our new results software in 3D, and we can actually view the hydraulic fracture formation in time, which helps us analyze the hydraulic fracture formation. And so with this new tool, we can optimize the hydraulic fracturing process from the pressure to the amount of fluid we inject, and also the fracture spacing, by taking these hydraulic fracture models and then performing forecasts on them. And then we can take those fractures and we can perform operational optimizations on them, for example, or we can evaluate different EOR processes on them as well. So when this new hydraulic fracture initiation and propagation tool is combined with our existing unconventional workflows and our CMOST AI software, this makes CMG the only software suite that can model and optimize the entire life cycle of an unconventional well. So the geomechanics module that we talked about on the previous slide has been available in CMG for over 10 years now, and we've continued to improve on it and develop new features. We talked about one new feature on the last slide, and a second improvement in the area of geomechanics is to the Barton-Bandis model. And the Barton-Bandis model is another way that we have to estimate the hydraulic fracture formation within our reservoir. And so the change for this year is the fracture opening criteria that the Barton-Bandus model uses can now be defined as a change in minimum effective stress instead of an absolute value. So that change is defined as the current value of minimum effective stress in each grid block minus the initial value. And this new option is better aligned with the case where you have an initial stress gradient in your reservoir, because potentially if you had an initial stress gradient, meaning you have a different stress in each grid block in your reservoir, you may need to input a different absolute value previously, whereas now you can just input the uniform fracture stress change for fracture opening to occur. And so this new input is better aligned with sometimes what exists in reality in our reservoirs, and also with the data that's available for us from the field to input into the reservoir simulator. Another step we've taken in improving our unconventional and hydraulic fracture modeling workflow is the addition of the planar fracture connections option. So now the hydraulic fractures that we create in our models, if they're adjacent to one another and they have half lengths that overlap one another, we can make them seamlessly connect for a continuous flow channel between the wells. So for example, on the image shown on this slide, we have two horizontal wells that have been hydraulically fractured with several stages. And the first hydraulic fracture stage, which is at the toe of the wells here, are lined up perfectly adjacent to each other, and they are very long half lengths, so they could potentially overlap with each other. And previously we would have seen a small gap exist between these hydraulic fractures, whereas now we have the ability to have those hydraulic fractures seamlessly connect. And this is an option, so we could leave the gap or we could have that seamless connection. And this really allows engineers and users to test their theories of significant interwell communication that might be occurring due to the hydraulic fracture connection and achieve better history matches as well as more accurate forecasts. This next feature is one that we've been asked for a few times from clients recently, so we're happy to say that we've listened and we've implemented a new option called formulaic triggers. And if you're not familiar with triggers, you could think of them as sort of if-then statements that we can use to dynamically control our wells or our groups or our reservoir in time instead of just specific actions on fixed dates or times. For example, you may want to open an injection well once your average reservoir pressure declines below a certain value, but you may not know exactly when that value is going to go below your threshold. So instead of trying to guess when it's going to occur, you can use a trigger, and you can just say, if my reservoir pressure goes below this threshold value, then open my injection well. So that's just triggers, and we've expanded on this in 2017 to allow for mathematical expressions as well as multiple variable dependencies to define the conditions when the trigger will actually take action. And this is best explained through an example. So I have one shown on the screen here. But keep in mind that this is a very open-ended way of defining what controls you have to your reservoir. So the combinations or the scenarios that you could use to control your wells or your reservoir now are almost limitless. But for example, on the screen here, we're showing a SAGD injection well here with two injection points. We have one at the heel and we have one at the toe. And typically in this sort of scenario, we want to make sure that at least two constraints typically are being followed. The first constraint is we don't want to inject at too high of a pressure because we have to stay below the regulator dictated maximum operating pressure. And second, we want to make sure that the injection volumes are set to roughly half or 50% of the total well out of each of these strings, or maybe some other predefined ratio. But typically we don't want to have 99% coming out of one string and just a small volume out of the other. So we can actually do this now with formulaic triggers fairly easily. And how we do this is we would set the heel string here to a bottom hole pressure constraint. And from that bottom hole pressure, the simulator is going to determine an associated steam injection rate. And we don't know what that steam injection rate is going to be, and it's almost certainly going to change throughout the simulation. And it's going to change because of what rate or pressure is coming out of this toe string here, and also based on what the steam chamber might be encountering at the time, and also definitely based on what the producer is doing. So instead of trying to guess what steam rate we should apply to the toe string, we can actually use a formulaic trigger to control that and make it variable and depend on time. So what we can do to set this injection rate at the toe is we can say Q steam 2 at the next time step, or the steam injection rate out of the toe string at the next time step is equal to the sum of the injection rates from the current time step out of each of these strings times 0.5. And so by doing that, we'll get roughly a 50-50 split out of each of these strings, as well as make sure that we stay below the regulator dictated maximum operating pressure. And again, this is just one example, but you can make very complex and very complete reservoir controls using this new formulaic triggers option. In 2017, CMG has a brand new manual format for every product available in our software suite. So our user help manuals are now going to be shipped in HTML format, which is a web page based format. And while upgrading and changing the format, we've taken the opportunity to also increase the usability of our manuals significantly. And we'll talk about two main areas where we've improved this today, being searching, which is shown on the left image here, and the readability of our software page, or sorry, help pages, which is on the right side here. So in terms of searching, we've improved the search results in a few ways. First, we've created keywords or phrases that are linked to certain acronyms or something. So for example, on the left side here, we're showing we've searched for FHF, and that stands for Field History File in CMG software. And so the actual words Field History File are linked to that acronym FHF, which helps you for searching things. Also, the frequency of the search results, so the amount of times that it shows up in whatever page that you've got at the top of your list here, the number of times it comes up is going to rank these in the list here. So the more often it comes up in a page, the higher it'll be on the list. And also the location of where your search result shows up will also matter. So if we were to search again FHF, if it were to show up in the title or the heading, it would be ranked higher than if it were to show up in the body of the text. And moving over to the readability improvements, the main way that we've improved the readability of our manuals is through something called high resolution pop-up images. So previously, images were always the same size in our help manuals, whereas now when you first go to a manual page, the image is going to show up very small, and that helps the readability of the text kind of be maintained. You don't have to scroll as much through big pictures. And if you actually want to look at that image, you can click on it, and a full high resolution image is going to pop up, which would be clearer than it was in the previous help manuals. So when you're done looking at that image in high resolution, you can click it again, and it's going to expand back down, and then you'll be able to continue reading. And so we've just talked about two of the areas where we've improved the usability. There are several new upgrades and features to our help system. Again, you can find some more of those in the software highlights document, or this being a web page-based browser, or sorry, a help manual, you can add it to your bookmarks or your favorites of your browser once you install it, and you can just take advantage of all the usability features by starting to use these new format of the manuals. Next, we'll talk about some of the improvements for IMEX this year. So a few slides ago, we talked about the geomechanics options, and the geomechanics module has been fully integrated and added into IMEX this year for when black oil fluid models are sufficient. So all of the options that you may be familiar with from using our GEM simulator and all of the non-thermal options from STARS, as well as the options that we just talked about that we've introduced this year, are all available in IMEX as well now. So for example, just a quick example of geomechanics. In this case, we have shown on the screen here, we have a primary depletion scenario in which the bulk volume of the reservoir has collapsed. And that was predicted using geomechanics. If you don't use geomechanics, then the bulk volume is assumed constant. And so in this case, we can estimate using geomechanics how this collapse in the bulk volume is going to affect our recovery, as well as our pore pressure. And we can also analyze whether or not the reservoir rock is going to yield or break. And also we can analyze the rock above the reservoir, potentially all the way up to surface, to see if it's going to yield as well. Next, we'll look at a couple of new relative permeability options that have been added to IMEX this year. The first of which is table-based relative permeability endpoint scaling. And this method of endpoint scaling for relative permeability is particularly useful if you've built your reservoirs using facies or rock types. So for example, on the screen here, we have shown on the right side a reservoir that has 5 different facies or 5 rock types. And for example, the engineer may want to change the relative permeability endpoints for just one of these facies. So instead of having to define the same endpoints for all of these other grid blocks and change only the one shown in red here, the engineer could use table-based scaling to scale only the table that's applied to these red blocks here. So it's a lot more convenient for changing just specific areas of your model. There's also a new keyword defined called copy, which lets you, of course, copy rel perms from one table to another one, and then when used in combination with the table-based endpoint scaling, you can quickly define relative permeability sets that have a similar shape. For example, they might all follow the Corey equation, and they just have different endpoints. And so these 2 keywords are very useful if you're building models, again, based on facies, or definitely in certain history matching workflows. It can be quite useful and quick as well. New to IMEX this year is the option of relative permeability interpolation. And this option is already widely used in our compositional simulators, GEM and STARS. And so this new option lets us make our relative permeability depend on other parameters than the traditional phase saturation. And in IMEX, we can make our relative permeability depend on 3 additional parameters currently. The first parameter we can make it depend on is the polymer concentration. So depending on how much polymer we have in a grid block, we can adjust our relative permeability to water, which is very important for accurately modeling polymer injection processes. And we've also made another improvement to IMEX this year for polymer injection, which we'll talk about on the next slide. The second dependency that we can make the rel perm depend on is the seawater volume fraction. And so again, depending on how much seawater you have in a grid block, we can adjust your relative permeability, which is very important for accurate modeling of low salinity water injection processes, for example. And finally, we can make the relative permeability depend on the light oil volume fraction. So in this case, in IMEX, we would have a light oil and a heavy oil, and we could make our relative permeability depend on how much of each of those different oils was in each grid block. For example, if we had more of the light oil, we could have a higher KRO, and if we had more of the heavy oil, we could have a lower KRO. So the second enhancement that we've made for this year in polymer modeling at IMEX is the inclusion of shear effects on determining the aqueous phase viscosity. And we've included shear effects by using the shear thinning and shear thickening power laws when we have polymer and water mixing to determine the viscosity in the aqueous phase. And so we have this represented by this image on the slide here. So previously we were only able to model this green line, which is Newtonian fluids, meaning that we have a linear relationship between shear stress and shear rate. And the slope of this green line is the viscosity, and it passes through the origin, whereas now we can define the shear thinning and shear thickening relationships through the power laws to take advantage of more of these more complex physics and more complex polymer viscosity relationships using IMEX. And so when we use this new option combined with the relative permeability interpolation based on polymer concentration that we talked about in the last slide, it makes IMEX a very powerful tool and much more accurate for either modeling polymer projects in entirety or for accurately screening polymer flooding feasibility before taking it to a more advanced simulator, being one of our compositional stars or GEM simulators. We've also made a couple of initialization, fluid initialization improvements for this year. The first of which is the ability to better model tilted contacts. And so now we can actually define a pillar-based water contact map using a grid array. And what this means is basically each column in our model, so each IJ block, can have a unique either water oil or gas oil contact. And this lets us essentially import contact maps to define some of the more unique and complex fluid contacts that we might have in the reservoirs. A second improvement is the user can now specify the number of points that are used in the property versus depth fluid initialization calculations. So essentially the number of points would have been determined internally by the simulator previously, whereas now the user can define more points. Typically, you would use more points, and of course a higher resolution depth table can provide better representation if you have very nonlinear phase pressures or properties which typically happens if you have a very large depth range represented by your model, or sometimes if you have a very significant gas cap in your model as well. So with the addition of these two options, it ensures that we have accurate initialization of our phase pressures, densities, phase saturations, as well as our capillary pressures when we're modeling using IMEX. Next, we'll go over some of the improvements to GEM for this year. So GEM currently has a very extensive modeling of reactions through its geochemistry reactions and its equilibrium reactions. And this year we've added another reaction model to GEM, being the Arrhenius rate reaction model. And with this new model, we can include temperature dependency on our reaction rates by defining an activation energy. And this is best explained through the image shown on this slide. So we have over here on the right side, on the x-axis, we have the reaction pathway, or the reaction progress, basically from the reactants on the left to the products on the right. And then we have on the y-axis represented enthalpy. So starting from the reactant enthalpy over here on the left, as we want this reaction to progress, we need to overcome this activation energy, or this EA, which stands for activation energy. And typically that would happen, or that would occur because the reactants were able to absorb enthalpy from the environment, which would typically happen because the environment had a temperature increase. So through this activation energy, we can model the temperature dependency of our reactions. And once we've overcome that activation energy, we can have the reaction proceed and form the products. And another feature with this Arrhenius rate reaction model is we can include sort of a time dependency on our reaction rate or our reactant concentration through the introduction of a frequency factor. And this is important for modeling processes such as polymer degradation, where for various reasons the polymer breaks down in the reservoir over time. So we can use a frequency factor, which is often determined by the polymer half-life. So over the last couple of years, GEM has undergone significant development to be able to better model enhanced oil recovery processes, and particularly ones that involve components in the aqueous phase, such as, for example, alkaline surfactant polymer or ASP floods. And so to help assist with this aqueous phase modeling, we have now extended molecular diffusion coefficients as well as convective dispersion to the aqueous phase in GEM. Previously, before we were modeling some of these advanced aqueous phase phenomena, we were mostly only concerned with the hydrocarbon phase or the oleic phase, and so we were only estimating molecular diffusion coefficients for the oleic phase, and there wasn't distinction made between water and oil. Whereas now in 2017, we have an additional option to use what's called the Wilk-Chain correlation for estimating molecular diffusion coefficients in the oleic phase or for hydrocarbon components. And then we can apply the Stokes-Einstein correlation for determining the molecular diffusion coefficients in the aqueous phase. CBM modeling has seen a recent uptick in simulation, and so we've added an option to allow for more accurate modeling of the CBM process. And the new option that we've added is the ability to model directionally dependent changes in the porosity and the permeability as the gas molecules desorb from the reservoir rock, which occurs during production. So currently we've had the Palmer-Mansouri model in our GEM simulator, which allowed for, we could model porosity and permeability changes as we produce and as the desorption occurs. But now we've added a more generalized form of this called the Palmer-Higgs model, which uses 3 Poisson's ratios, one for each of the I, J, and K direction, to account for the change in porosity and permeability in each direction separately. Next, we'll go over some of the improvements to stars. So in stars, we have the ability to apply gas-like properties to the liquid phase. And typically when we want to do this is when we have gas bubbles entrained inside of a liquid phase. And the most common time when we would want to apply this is if we have what's called a foamy oil. So if we have a very viscous oil or liquid phase, and then we drop the pressure below the bubble point pressure, we will have gas come out of solution, but before it can form a continuous connected phase, it's kind of trapped as little gas bubbles inside of this very liquid oil because viscous oil, because it takes some time for it to bubble up and form that continuous phase. So this is foamy oil, and previously we've had the ability to apply these gas-like properties to the liquid phase for modeling this to the flow properties, being viscosity and density. And we've taken this idea in 2017 one step further and extended it to the thermal properties, being enthalpy and thermal conductivity. And so with accurate modeling of both the flow properties and the thermal properties, we have a more complete handling of these complex fluids such as foamy oils. For several years, STARS has had a transient wellbore model fully coupled to our flow simulator, and this is called FlexWell. So we've continued development of FlexWell this year by adding an ability for the user to disable or enable phase segregation occurring within the well. And we've added this because depending on the scope of the study, not all of the models that you're using may require the full wellbore treatment or the full phase segregation. And so with this new option, you can tailor the complexity of your wellbore model to the specific needs or outcomes that you want from your project or your study. So when phase segregation isn't allowed in the wellbore, which I should say before phase segregation was always on, whereas now we can turn it off, which is represented on the right side. So when this is happening, basically assume that this is a wellbore and we have a production point on the left. So all phases have to move in the same direction when we have phase segregation switch turned off. So basically we can still have the three phases, oil, gas, and water, go at different velocities, and we can still calculate a slip between those phases, which will lead to a different Reynolds number and different pressure drops in our wellbore, but they do have to move in the same direction. Whereas if we do allow phase segregation, that's represented by the case on the left here. So again, we have a wellbore with an undulation, and let's say we have a production point at the left. On the downhill side, we'll most likely see all of the phases moving in the same direction. But as we move uphill, it's possible that the less dense gas phase will continue to move towards the production point, but the oleic and water phases, being more dense, could tend to pool at the bottom of this trough, which we do see happen in reality. And so in this case, we have phases moving in different directions, and we call this countercurrent flow. And this is, of course, a more complex wellbore problem to solve compared to the one on the right. So by adding this new option, we have a more complex case on the left and a more simple case on the right, which lets you tailor the complexity of your wellbore model to the specific goals or outcomes that you require from your study. FlexWell also has very rigorous heat loss calculations, and we've improved them this year by allowing the user to specify their metal tubing or annulus wall heat capacities and thermal conductivities varying along the length of their wellbore. So basically, this will let you model composite tubings where you have different properties or different materials representing your well along the length. We've also added the ability to make the heat capacity and thermal conductivity depend on temperature through a second order polynomial. So before, these would have been static values, whereas now we can have them depend on temperature and change with the temperature. And so these two changes just even further give more accuracy to FlexWell's heat loss calculations for accurate modeling of complex wellbore. IMEX is a powerful simulator by its own right, but often it's also used to screen processes quickly before they're taken to one of our compositional simulators for further analysis, which are typically considered more advanced. And so for these workflows, we need to convert between IMEX and STARS. And this conversion is assisted in several ways. One of the ways is we have a builder process wizard that will automatically convert all of the IMEX keywords in PVT into STARS PVT and keywords for you. And we've now streamlined the conversion process even further by making it easier to get an exact match between the two simulators. And this was done by aligning several options, mostly related to relative permeability between IMEX and STARS. So we have just 4 of the examples represented here. There are definitely more, which again you can check out in the product manuals. But just to go through a couple of them, we have saturation endpoint scaling. So all of the options that were previously available in IMEX are now also available in STARS. And we also have perforation-based relative permeability endpoints. And this is an option that's long been available on IMEX, and users sometimes like to change the relative permeability endpoints specific to each perforation or each well to get a better history match. And this wasn't available in STARS. In 2017 it will be, and so we can get a lot easier to get a match between the two with the same keywords available.
At this time, I'd like to pose a question to all the attendees is, how often do you numerically tune your models to improve the runtime and the performance of your models? You can click one of those options that is shown on the screen. And the 4 options are always, sometimes, rarely, and never. So we'll wait for everybody to respond in a few seconds here. The polls are coming. There is 64% people who have voted right now, and the statistics are being compiled. We'll give a few more seconds here so that everybody has a chance to respond to this question. We're close to 80% almost. So far, the trend seems to be 46% of the people who have responded numerically tune their models 45% of the time, and 30% say they always do. So good to see that majority of the users do try the numerical tuning options to improve performance on some of the numerically challenging simulation models that you guys are using. So hopefully the auto-tune and the combinative solver in the 2017 version minimizes the need to manually tune your models. And one keyword does help improve convergence as well as improve runtime significantly. So if you haven't downloaded the 2017 version, I recommend that you do download that version and try out some of the new features, especially the auto-tune on your models, and send us feedback. How did it work or perform on your models? So looking forward for your feedback on this feature so that we can continuously improve on this and make it even more valuable to you. Back to you, Greg.
Thanks, Anjani. So next we'll talk about some of the improvements to our CMOST AI software. And sometimes clients ask us what CMOST AI is or what it's for. So to try and explain it from a very high level, CMOST AI is a tool that will help you enhance your ability to do simulation work. And so CMOST AI uses artificial intelligence-based machine learning to apply its internal algorithms to assist engineers basically get a better answer and get that answer faster, whether they're trying to perform a history match or an optimization or any other workflow that CMOST AI assists with. And also CMOST AI provides a very important simulation results analysis section, which is very powerful for helping engineers identify the best solutions and to make more informed decisions and draw conclusions that they maybe wouldn't have otherwise been able to see. So the first option that we'll talk about plays into the machine learning role of CMOST AI, which is multi-layer neural network. And this is an additional method that we have of generating a proxy in the CMOST AI assisted workflows, such as history matching and optimization. So CMOST AI now has 3 proxy models available to help determine the outcome or the effect of changing parameters on objective functions. The first one is polynomial. The second one is RBF neural network. And the third is, of course, the newest one that we're talking about now, which is the multi-layer neural network. And this allows users to use either the default network, which is sufficient for many problems, or more advanced users of CMOST can define their own network by defining the number of layers in the network as well as the number of nodes. And our test results show that with the appropriate network configuration, the new multi-layer neural network can provide more accurate proxy modeling compared to RBF. And also, once the proxy model is built, the multi-layer neural network is faster to predict the outcome than RBF. If you're not aware, CMG has developed an entirely new results storage format. So this new format is called SR3, and the previous storage format that we used was called SR2. And the benefits of this new storage format are, firstly, the files are a lot smaller in size. So the file sizes that we're seeing are typically half the size compared to SR2, or in some cases even smaller. And with this more efficient results storage format, we also have a lot quicker loading when you want to open up those results and analyze them in our results software. And finally, there's less files. There's only one result storage file created when you use SR3, whereas previously we had the IRF and the MRF files in SR2. And so in 2017, this more efficient format is now fully integrated into CMOST AI so that you can take advantage of all of the time and storage savings that come along with it, which is very important for CMOST, where we do sometimes tend to create lots of runs. The storage size is much reduced and loading of all those files is much reduced as well. Geological workflows that are carried out in Petrel can now be incorporated into CMOST AI's automated dataset generation and submission. So if you want to run a Petrel workflow when you're generating models using CMOST, first you're going to start CMOST AI, and from its CMM file or its CMOST master file, it's going to start building a data set. And then simultaneously, it's going to launch a pre-simulation command to silently execute Petrel in the background. And within that pre-simulation command, it's going to specify which Petrel workflow specifically you want Petrel to carry out. And then once both of these are done executing, Petrel will have generated some include files for you, most likely geological realizations being permeability and porosity include files. And CMOST AI will have finished creating its part of the data set, and it will put it together to create one complete data set, and then it's going to submit that to the simulators so that CMOST will run it and then perform its analysis. So this new workflow with automated Petrel silent execution makes it a lot easier to incorporate different geological realizations into our CMOST AI workflows, as well as reduce geological uncertainty in our modeling. And as I mentioned at the beginning of the section, part of CMOST AI's strength lies in its assisted analysis section, where it can present the data from sometimes hundreds of runs into single digestible plots that would otherwise take a lot of time to make or perhaps never get made. So this feature or set of features is built on and expanded for the 2017 release with the addition of something called stacked bar charts, which can show individual terms contributions to a total value if you're looking at field NPV or global history match error. So for example, we have this new stacked bar chart shown on the slide here. On the y-axis, we're looking at field NPV, and on the x-axis, we're looking at experiment ID, or basically each simulation test that CMOST submitted. So we can see from the top of where these bars all sit, the total value, which is the total field NPV, and then we can also make out from the same plot the relative contribution of each of the terms that contribute to the NPV. So in this case, we have 3 different wells contributing. We have well 1 in gray, well 2 in dark blue, and then our old wells in the light blue. So we can obviously from this make out easily how much each new well changes the NPV compared to what the old wells are doing. And this is for field NPV. We can also make the same type of plot for global history match error, where you could see if one well, for example, was a particularly bad offender for contributing to the history match error, you'd be able to easily see that from the size of its bar that it's creating for the total global history match error. And so from this new type of plot, we can get more information and better information from a single plot than we previously could. Next, we'll talk about the improvements to Builder. So as I mentioned at the beginning of this presentation, the dataset trends have been moving towards larger and larger datasets, and also the biggest datasets that we see have much more grid blocks as well. And then also there's more components and just more data overall. So along with trying to improve our simulator performance, we're also trying to improve our pre-processing performance or our builder performance by making sure that we can open and modify and then save and close these very large complex data sets in a reasonable amount of time. So on the screen, we're showing currently the load time improvements of Builder from the 2015 version to the 2016 in green to 2017 in purple. And we can see the loading times have been greatly improved. We're seeing these large complex models open in about a half to a third of the time in 2017 compared to the 2015 version, which has been a big focus for a couple of years. You can also expect improvements in the 3D interactions for several aspects of 3D visualization when you're looking at these very large complex models. So overall, you should experience less choppiness if you're zooming and rotating in 2017, as well as better visualization for wells, particularly if you're looking at the well perforations or the well trajectories, again in 3D view. So Builder has many guided tasks built in, which are very useful for assisting user workflows that require a lot of data entry or data conversion. And for example, completing model definitions for very complex fluids or very complex processes might require a lot of data conversion from what comes from the lab into what the simulator accepts. So in 2017, there have been process wizard improvements in Builder to help support the building of GEM and STARS process models. And so in GEM, we've added two new process wizards, one for the low tension gas flooding and another for the foam flooding or foam injection. So again, if you're modeling these processes, we now have a wizard and Builder, which are going to help you more easily create these data sets from the PVT to the RELPerm data and anything else that might go along with them. And then in STARS and GEM, we previously had polymer injection wizards existing, and these have been improved for this year with the ability to include additional relative permeability effects into the wizard. And then also for these polymer injection process wizards, we've added a lot more plots to make the analysis and QCing of the match between your lab data and what you're putting into the simulator a lot easier, and to make sure that you're maintaining the data that you have from the lab when you move it and convert it into the simulator format. For the last year, CMG has been providing quarterly releases for its results software, which is the newest version of our post-processing software. And these releases have been bringing results up to speed with its predecessors being Graph and 3D, as well as adding a lot of new features along the way. And so between the 2016 general release, or last year's release, and this year's, this process of upgrading and updating is complete, and the 2017 version of results can now entirely replace its predecessors, Graph and 3D. So of course, there have been many changes that have been made to results in order to make this happen. And in the following couple of slides, we're just going to outline a few of the key features that haven't previously been presented in depth. But for more information on how to use our new results software, please refer to our webinar titled Results, Faster, Intuitive, and Brand New, which is available on CMG's website. Or also check out the how-to videos on CMG's YouTube channel, which go through some of the workflows and processes of the new results software. So one of the key areas where the results tool has improved the post-processing is in the dashboards area. And dashboards provide an area for you to create synchronized views from multiple sources. And so we're showing a dashboard on the screen here. So this is one page that we would see in our new results software in the dashboards area. And we have 4 different views that we're looking at in this case. But you can control that as well if you wanted to look at 9 in the 3x3 grid, or if you wanted to just look at 2, you could do that. But we have 4 in this case, and on the top left and right, we have 2D plots. The top left is showing a well's oil rate, and then we have well bottom hole pressures for 3 wells shown here on the top right. And then bottom left, we have a 3D reservoir view and then a 2D reservoir view on the bottom right. So we have multiple sources of data in one page here, which is very useful. And also, all 4 of these are synchronized in time. So if we were to change the time that we were viewing, or if we were to animate this in time, we would see the block properties change on these 2 bottom views. And then also on the top, we would see this red bar move along, and it would be synchronized to the time that we're looking at in the reservoir. And this is very useful because we can analyze what our wells are doing or what our groups are doing at the same time as analyzing what's happening in the grid blocks around them in the reservoir. And in 2017, we also have the ability to save these user-created dashboards through something called dashboard templates. And basically, these templates let you save any dashboard that you've set up and you like and you want to use again into a template file. And then every time you open up a new SR3 and a new session of results, it's going to have that automatically created for you so that you can spend less time building these and more time analyzing your results. Another key advantage that the new results brings is the ease of use of our 3D analysis tools. And the main objective of this new filtering interface is to make it easier for users to define and manipulate and combine these 3D filters. So this new 3D filter window is shown in the foreground of this slide in the gray box here with the tiles in it. And when you go to a 3D view in our new results software, this analysis interface is going to be shown by default. And from here, we have all of the property filters, or sorry, 3D filters that were available in our previous software, but they're all available in one place that's easy to access and easy to create and change these filters. So for example, all of the different filter types are represented here. We can have property filters if you want to look at only grid blocks within a certain property range. We have custom slabs if you want to look at certain just sections of your reservoir, or we have this well slab tool, for example, which will let you view a certain number of grid blocks around each well. And then moving to the left side of this, this is a summary of all of the filters that we have currently defined in our session of results, and we can easily see which filters we have on. We can either activate them or deactivate them by checking or unchecking these boxes, and we can of course remove any filters or add new ones from the selections on the right here by clicking Add Filters. So essentially with this new analysis tool, all of the 3D filters are easily accessible and can be created and combined on the fly, which is a big advantage compared to our last Results 3D software. As I mentioned earlier, we have a new results storage format called SR3. And the previous storage format called SR2 can now be opened in the new results software. And this is a really big step because it means that all of the old simulation files that you might have on your servers don't have to be reran in the new simulators to be able to still view those results. Instead, you can just click your IRF file, which is the previous storage format, and drag it onto the results tile, so you can just open it like you always would have, but in the new software. And it's going to actually convert your SR2 files to SR3 for you. And this is a lot faster than having to rerun the simulation files by orders of magnitude. And so once that conversion is complete, you can choose to either keep your old SR2 files, or you can delete them and take advantage of all of the things that the new format and new software brings, such as faster load times, smaller storage size, and usability improvements. So this conversion is done entirely behind the scenes, and you only need to do it once for each set of SR2 files. Next, we'll talk about some of the improvements to WinProp. So I mentioned earlier, we have several improvements that have been introduced to GEM recently, especially around chemical EOR and aqueous phase modeling. And so WinProp has been upgraded as well to be able to better assist users in generating the simulator inputs that they require for these GEM processes from the lab data that they might have. So the first area we'll talk about is WinProp's improved accuracy of interfacial tension, or IFT, predictions by treating the vapor and oleic phases separately when they're being mixed with the aqueous phase. And again, previously we were mostly only concerned with the hydrocarbon component vapor-liquid interactions, or interfacial tensions, and those were estimated accurately. But now we've added additional correlations to predict the vapor-liquid interaction for aqueous components, which helps us model these chemical EOR processes in GEM better. And additionally, the predicted interfacial tensions can be visually displayed in WinProp now for much easier analysis in QC. We can make sure that the values are reasonable, and we can make sure that our curves are smooth without any jumps, which can cause runtime issues later down the road. And so we have an IFT versus pressure plot shown on this particular slide, and we can also create an IFT versus temperature plot as well. So we have three more options here where WinProp has been upgraded to be able to assist users with GEM PVT creation. The first two are dealing with carbon dioxide and hydrogen sulfide. So the first one here is we have improved prediction of the solubility of carbon dioxide and H2S in water for Henry's law. And basically the Henry's constant correlation for these two components, CO2 and H2S, has been extended to be accurate over a much larger range of pressure and temperature than previously was available. And secondly, we've added a temperature dependency to the binary interaction coefficient estimation between carbon dioxide in water and hydrogen sulfide in water. We have So this option that we have, as well as the one we talked about on the previous slide, are available here in this window, which is a screenshot of WinProp. And basically, this is the GEM simulator PVT output page in the aqueous phase page. And we have the hydrocarbon aqueous IFT calculation that we talked about on the previous slide. If you want to take advantage of that, we have some more information for it here. And then we have this checkbox to use it. And then the two that we just talked about, CO2 options and H2S options, we can use the Henry's law constant and temperature dependency options there. And then finally, the third point there, we have 3 reaction databases included in WinProp now by including 2 new geochemistry databases. And again, these are mostly for modeling chemical EOR and GEM. So we find it's a lot easier for users to just import a database from WinProp into GEM than to try and create your own databases manually by defining a lot of components and a lot of reactions and intermediate reactions. When we're trying to tune an equation of state using WinProp, we're always going to have one or more parameters that are being changed in order to match our experimental data. And this is a very common workflow when you're using WinProp. So analyzing the changes in experimental error when you're changing the parameters within WinProp was previously done through text in a table format, whereas now it can be carried out through something called regression plots, which represents the error in each experimental data point, both before and after the regression. And this change makes it a lot easier for analyzing your experimental error and your regression, as well as faster to find, because before that text table may have been in a somewhat large text file. So we have an example here shown on the screen of the new regression summary plot. And in this case, we have 5 experimental points for viscosity. And then we have the red bar showing the before regression error and the blue bar showing the error after the regression. So we can easily make out right away from this new plot the relative error, and we can easily see that we have 4 of our experimental data points have a lower experimental error, and then we can see how large those errors are relative to both before the regression and to each other. So we can easier analyze our regression results. Finally, we'll talk about cEdit. And if you're not familiar with cEdit, it's a relatively new text editor that CMG has developed internally for making editing our simulation files as quick and as easy as possible if you're using text to do that. And in 2017, cEdit has a new ribbon-based interface, which makes it more familiar and more intuitive to use. And this ribbon-based interface has 4 different tabs available, shown at the top here. And then we have File is the first one, which just lets us do regular file operations such as save and save as, open or exit. And then we have the other 3 tabs represented here in these 3 images. The first of which is the Home tab, which is the main tab that we have for editing and searching files. And a couple of examples of how cEdit can make dataset editing easier are, first we have this comment and uncomment line sections. So previously, if you had a large chunk of text that you wanted to comment out, you would have to add the 2 stars in front of each line. Whereas now, if you were to just highlight all of those in cEdit and then click comment lines, it would comment them all out with 1 click. And then you could, of course, remove those using the uncomment lines button. Moving to the right here, we have these bookmarks tabs. So bookmarks are very useful if you have a very large data set and you need to go back and forth between 2 or more places. For example, maybe you want to copy data from a well that's defined on the first date to a well that's defined at a much later date. Instead of having to search or scroll back and forth between those, you could set a bookmark at each, and then you could just go between those 2 bookmarks quite quickly. Continuing to the right, we have this keyword description button here. And what this button does is if you were to highlight any keyword shown in the text, and then if you were to hit that keyword description button or F1 on your keyboard, it's going to automatically open up our web-based help manual to that keywords page. So of course this saves time and it'll just is much easier to access the help manuals this way. And then finally, we have this compare files button on the far right here. And this is very useful for getting line-by-line comparisons of 2 data sets. So just as an example of when this could be useful, perhaps you are having a problem with a particular data set and you send it to a more experienced colleague for help, and they fix the file, but they don't necessarily tell you everything you changed. You could compare line by line your original file to your new one to see exactly what changes they made. The second tab that we're showing here is the navigation tab. And this has been added again to save you time from having to scroll a lot. So all of the major dataset entry areas are in CMG files are represented here. So for example, IO control, reservoir description, and component properties. So instead of have to search for these things, you could just click one and it would take you right to that point. For example, if you wanted to edit a well, you would just click well and recurrent data, it would take you to that section, you'd more quickly be on your way. And then the fourth tab we have here is called CMOST. And cEdit is still the best tool we have available for directly editing in text our CMOST master file. So of course, from the CMOST tab, we can create CMOST parameters, we can navigate between our parameters, and we can also from this drop down either search for some or see all of the available ones that we have for searching. In this year's release, we also have more file types available to be opened and edited using cEdit. So cEdit started as CMOST's CMM editor, and then that its use was expanded to the builder datasets or the .dat files. And in this release, we can now open almost all CMG file formats, including the out files or our simulator text outputs, simulator include files, log files, as well as our WimProp PVT output files. So with the continued development of this relatively new product, we've brought about several usability improvements in this release as well. And we'll only talk about a few of them here. There are many more, which you again can find in the software highlights or the help manual for cEdit. So the first one we'll talk about is line numbers. So this is the actual text section that shows of cEdit if we were looking at a .dat file. And on the left-hand side here, we always show the line numbers. And then this year, the line numbers exactly match up with what would show if we didn't open this in cEdit, because cEdit is one of its great strengths is if we look here, we have the chord keyword, and then we have about 3,000 lines of grid coordinates. And so we know you most likely don't want to look at that every time you open the data set, so it's just collapsed into one line. But if we look at the Z-corn keyword here, it shows the actual line number being 3061 as if it weren't collapsed. And this is very useful because more often than not, if you get a warning or an error in one of your simulations, our simulators will give you the specific line number in your data set that caused that error or warning, so you can easily find the line number in cEdit that the simulator gave you so that you can easily fix that or at least know where the problem is coming from. Another improvement in 2017 is the addition of line modification markers. So whenever you open up again, data set in cEdit, any line that you edit is going to be highlighted here right beside the line numbers with this little yellow bar. And this is very useful for if you just want to keep track of all the changes you've made since you opened the data set or since you last saved. And then the third option here is find all. So when you search for something, you can find all instances of what you searched for, which is a common feature available in good text editors. So we've added that to cEdit as well. And then as we talked about a couple of slides ago, we can quickly navigate between lines containing bookmarks. That concludes my section of this webinar. If you missed us in the first few minutes, we talked about some pretty powerful new tools. So please be sure to download this webinar from our website and take a look at those first few options that we talked about.
Thank you, Greg. We are just a little over our allocated time, but it's totally understandable. If you have any prior commitments, you can exit the webinar, and the Q&As will be added to the recorded version of the video in case you are interested. So we will like to take on and continue and take on a few questions for people who are interested to know more about the things that Greg presented. So the first question is from James, and the question is, the geomechanics module, is it extra license and extra cost to the user, or is it included in the simulator by default?
So the geomechanics module is completely included. As long as you have a simulator license, you'll be able to use the geomechanics module for that simulator.
The next question is from Saida, and the question is that if I have simulation runs from versions prior to 2017, do I need to rerun the simulations to use the 2017 version? I can take that question. No, you do not need to rerun your models. There is an internal converter inside the new results which converts the SR2 files, that is the IRF and MRF files, into the SR3 format. And then you have an option to save it in the new format once you exit the new results. So the files are easily converted from inside. So the next question is from Kevin, and the question is, can I use auto-tune and some parameters that I want to apply manually in another data set?
Basically, it depends on if you're using stars or gem currently. If you're using stars, the answer would be no. Auto-tune is just going to take over the numerical control section to get you the best runtime possible. There is kind of a sub option in gem which would let you exclude certain keywords from being overwritten by auto-tune. So overall, I would say no, auto-tune takes over and will get you the best runtime possible.
The next question is, what is the difference between modeling of polymer in IMEX, stars, and gem?
So IMEX, as we talked about, had a couple of big new improvements for more accurate modeling. However, I guess stars and gem would still be our most complete modeling packages for modeling polymer injection. So some of the features or options that would be included in stars and gem compared to IMEX is stars and gem can model polymer viscosity versus salinity. And another area is polymer adsorption versus salinity. So basically, we have more salinity effects in stars and gem compared to IMEX. Stars and gem also have the ability to model reactions. So we talked about polymer degradation in gem through reactions. So that can be modeled in both stars and gem as well. And also, if you wanted to set up a somewhat automated study where you're evaluating different types of polymer to see which one would be the best, you could define multiple polymers in stars and gem and just inject one at a time. Whereas in IMEX, you only can define one type of polymer.
The next one is from David Brock, and the question is, does the auto-tune keyword gives any feedback that would guide a user on making additional manual numerical tuning to a model? I can take this one, Greg. The auto-tune is based on AI and it's adaptive. So basically, it learns from the simulation as the time stepping progresses, and internally actually evolves and learns from it and makes dynamic changes to the numerical tuning parameters. So the numerical tuning parameters would be changing with time internally in the simulator based on the adaptive algorithm. So the whole idea is to take the manual intervention out of this workflow, and the one keyword that you put in the data set takes care of everything. Another comment that he has is, and that's so nice of you, David, that it's a pretty good feedback regarding the new results. The comment is, the results dashboard is a nice feature, particularly the full coordination of all the views in time. Beyond being a nice graphics reporting feature, it is a good analytical feature. So thanks for that sharing that good feedback, David. There are several other questions, but just for the sake of time, what we will do is we will respond with these questions individually to each one of you within the next 24 hours and get back to you with the details. So there are around 300 new features in the general release 2017. So if you haven't downloaded it, do download the new version and try it out and provide us feedback. If you want to know or learn more about new features and capabilities, or even like process modeling in our different simulators, we offer several training classes on various subjects around the world. So I invite you to check on our website on the training page, and if you're interested in attending any of our training courses, then do register and let us know. Again, I like to reiterate that the recorded version of the presentation will be posted on our website within the next 24 hours. It will also be available on our YouTube channel as well. You'll need to log in using the CMGL username and a password to access the material. If you have any other questions related to the material presented today, you can contact us at sales@cmgl.ca and we'll get back to you. So again, thank you for joining us for this webinar on what's new in the general release 2017.